Hey, my name is Ryan. I'm an electrical engineer. I studied at RIT, and I'm going to take you through an end-to-end design process speedrun using Flux Copilot. To start it off, typically at a company or a larger, let's say, startup setting, you'll get the requirements from a meeting where people look at the product roadmap, you understand the need of the customer or the problem that you're trying to solve, and you go from there. I think this is what we're going to be doing today, which is speedrunning an AI pendant. There's been a lot of buzz about AI pendants from a bunch of different people, a bunch of different companies, and I think it's the interesting concept, having something sitting in your lapel, recording your conversations, taking all of this audio sensory input and organizing it into something that you can sift through. I know firsthand experience for most of my career, I would have liked to have something that I can fine tune in what it takes and records in terms of my conversations one-on-one. Oftentimes I'll go into a conversation, be really excited, and then quickly after, once I get moved on to the next thing, I lose a lot of the meaning and a lot of the action items that I should be recording. So this is a potential solution for one of these, for exactly that situation. When you open up your first Flux project, you're going to be met with your homepage. I'm on my start tab because these are the things that I don't mind you guys seeing. You can see I have quite a bit of projects, most of them unfinished, a lot of them for testing purposes. But in this case, we're going to do end-to-end. We're going to get this board done and we're going to speed run it. It won't be the fastest thing ever, but it will be faster than most products are developed. And that's because we can use AI, leverage that to assist with the entire design process from beginning to end. And I'll show you highlight exactly what I'm talking about. Let's say we're going to start off the speed run with something it's a wearable, it's an AI pendant. It's also an IoT device because we can't expect all of the data and the human interface to be on this AI pendant. You have to interface it with some kind of more robust system like your phone or your laptop in order to access the information that's been organized by the AI that's running on the pendant. I'm going to go IoT wearable. You can see I have a bunch of these because I really enjoy making IoT devices. I think they're a great place to put your skills. I've also roughed out the way that I wanted to start this beforehand. I'm going to say the speedrun starts pretty much when I get into the project and start interacting with the AI agent. But yeah, let's just start with this template, IoT wearable. Sounds good to me. What this is going to be doing is just preloading with some information. You can see in your Flux dashboard as it stands, you're going to have your library, you're going to have the objects that are on your actual canvas. Library is a public library where anyone can post whatever projects or components they make, modules, and you can slide it over and look through it. Now, a lot of these are generic things like power portals, ground portals, net portals, generic resistors. If you don't want to spend the time making your own component from scratch, you can just use a generic resistor with the right footprint. That's totally fine. But there's also specific MPNs in here. And the coverage is pretty good. We're going to put it to the test, especially if you use something obscure like an obscure audio codec, which is probably something that's going to happen. Knowing how the system works, it tries to optimize based on your requirements, not based on some ephemeral, like you're thinking that it should be this, but it actually is this. You have to define what you need. It only works off of the information that you provided. So before we even launch into Copilot, we want to set up this project, really round out this template. What this template does is it gives you this image and then defines some of these properties in the project description. So we can go through these. I'm probably going to use something more like Python. Python's better for just embedded AI all around. I have a much easier time programming with that. Connectivity, USB, Wi-Fi, Bluetooth. Yep, all that makes sense, especially for charging. We're going to want to use like a USB-C charger. Wi-Fi, maybe Wi-Fi. Let's leave the option open. I know there's a lot of microcontrollers that use both Wi-Fi and Bluetooth. So we'll keep that. Yep, that works for me. Let's knock it down to 3.3 volts. It's just more common of a microcontroller voltage. Antenna, definitely PCB trace, although if I was making a full product, I would actually go with an antenna, just a straight up antenna. PCB trace antennas are nice, but it doesn't really give you the same control, especially when something's right up against your skin. It's going to affect the radio itself. You might have a more difficult time creating a PCB trace antenna if you have to model the skin, the clothing material. It would just probably be better if you had more control in the positioning and the angles of the antenna. So I'd most likely not go with PCB trace if I was making a real product. But for this case, I'm really trying to speed run this and I want to prove the concept. If it happens to mess up with the Wi-Fi and I don't get as good power transmission, then that is okay with me. I want something on the canvas and on a PCB, human interface. Let's do something very simple like an RGB LED ring. It's going to be pretty power hungry. Maybe I'll change that later. And a button, because buttons are fun. Reliability, sure. Let's do that. Wearables, absolutely. Number of sensors. For an AI pendant, we only really need something to take in the audio, process it, do its AI configuration, whatever algorithm I end up settling on for the speech to text, it needs to be able to handle that. But in terms of sensors, it seems like it only needs 2. 3, if you include the button. I would say the button is a sensor of sorts in this case. There'll be different clicks. It's a digital sensor. Come on, why not? So 2 microphones and 1 button. Oh, wait. Let's actually set that to 3. And let's do that here. Cool. Consumer electronics. Yep. Battery. This is going to be a tough one. We need it to fit in the form factor. Not really sure what that form factor is going to be, so I'm going to roughly estimate this at... This device should be able to operate throughout the entire day, at least the entire workday. The times where you really need it are when you're going into meetings, so maybe you can activate it then, and then once you're out of the meeting and going to do your designing a PCB, if you're an electrical engineer or what have you. So perhaps I'm going to do a little adventurous. Do 2,000 milliamp hour. Let's do a LiPo for its size relative to energy density. Okay, now we're going to open the chat tab. I think I said previously that I have a description already made for this. I'm going to try and leverage AI to maybe make it a little bit more optimized for AI. AI optimized by AI. Let's do this. I'm gonna grab that real quick. Okay, and now so what this is going to do is I'm now talking to Copilot. Copilot is the AI agent that is in every Flux project. It helps you in general things such as block diagrams. If you wanted some code, if you wanted to write some embedded firmware using the data sheets that are in your project, really helpful. You can query pretty much any information that is on your canvas locally, as well as some part information that we can get into later. It's a really powerful agent, and there are multiple different versions. There's the one that's for help, so if you need some help in Flux documentations, we got you. There's an agent for that. If you want a librarian, someone who can go into the data sheets, extract the information that you need, and deliver it in a, maybe you're asking a question that's a little bit more complex and requires some additional information external from the data sheet, or you just don't want to go look for that information, you got librarian. And then if you want something that's more general, I think, like I said, this is the generalist. He, she, they, it's able to, get the information that you want based on the questions. All of them operate with the same principle. The more information, the better the results. And I think that's how we all operate. Let's take a look. Let's see. Text recognition, power consumption, efficiency. Add to the description. I have it append its description a little bit with some information that I just thought of, which is to have the battery life be around 6 hours. I think that pretty much encompasses an entire workday, at least the parts that you're going to talk, maybe more than you need, hopefully, unless you're working at a startup and you work 12 hours a day, in which case it will absolutely not do enough for you, and you'll just have to activate sticky keys by accident. All right, let's do AI edit. Edit speed. Let's do speed. Now that the project description is all set, it's time to start designing. The first step is to do architectural design. We're going to want to do a functional block diagram, navigation, use AI to ping pong some ideas off you for general architecture. Seems pretty straightforward, but I'm curious to see what the results may be. Generate, let's make sure that we activate Copilot. We're going to still use the generalist. Actually, no, let's use the librarian. I think the librarian might have some insights on parts even before we ask it for them, which will be step after. This architecture seems to be like a battery, power management IC, a great microcontroller, great Bluetooth module, Wi-Fi module. We'll combine these in the microcontroller, 2 microphones, activation button. Let's see what the next one is. LiPo, BMS, charging. This one, okay, fair enough. I do need a charging circuit and a power management IC. Hopefully I can combine them. Let's see. We got activation button, signal processing unit, very important. Let's move the codec, and this one. You know what? It's so small, we might as well open it in a new tab. Okay, so we have all the same things. And then AI processing unit, audio analysis module, information filtering module. So based on this block diagram, we have a good idea about what the power tree is going to be. Now I guess we can start coming up with some parts, right? You have a block diagram, you like it, gone through the back and forth of negotiating with your requirements and what you can see is the best architecture. It's time to start defining what these blocks actually are. Let's start with the brains of the operation, the microcontroller. Not exactly sure if it takes SVGs. I know it takes images. Worst comes to worst, I'll screenshot this. But the goal is to work on multiple things at once because we want to speedrun this thing. Let's see if that worked. It might not have worked. I might have to take an image, but that's okay. For now, let's take a look what it came up with. It seems like this ESP32 is a good option, but I would love, figures. I'll take a screenshot of that block diagram and send it in, and then we'll work in parallel on some of these. I have downloaded the image, uploaded it, just took a screenshot the same way I did before, and there we go. While that's going on, I asked it previously to compare the ESP32 versus the ESP32 ROM 32. I don't know if I'm pronouncing that right. WROM, WROM, core, enhanced security features, comparison processing power, better performance and power efficiency. I like that, especially on a wearable memory. Let's see, we have, oh, and by the way, I'm going to be using the ESP32 S3. I think that's going to be a better for both power efficiency reasons and for AI computation reasons. We can really pull some learnings out of this right now. Let's do a yippee moment. A yippee. It works. It's considering all of the design requirements, form factor, power usage, everything that we set up in the project description, everything that we set up in the block diagram. It's using all of that information, combining it together, and then it's able to evaluate pros and cons, trade-offs of different components and provide us different MPNs. Typically, this process would take a long time. And I'm not saying that we're not going through the whole landscape that we could possibly use to optimize this project for production. That's true. But again, we're trying to get this off the ground. And I tell you, architecture exploration, especially when you don't know a lot about a specific family of ICs. For example, I'm not an expert in audio codecs. You ask me anything about I would say an ADC, right? Who doesn't know an ADC? Let's go for that one. Audio codecs, not my thing. Having something that has a wide landscape, a vast landscape of knowledge about a broad number of things, very helpful. And it even has some pretty exact information once you get that data sheet in there. Okay, careful PCB layout. I don't know if that's necessarily going to be the best option for us, considering we're gonna have an antenna right there. I'm not too worried about antenna interfacing with, but I don't want to go through the whole desense process and find out that my radio is causing problems on my audio codec, and I'm recording the actual transmissions to my phone rather than the conversations in front of me. So for all these reasons, and without asking for 3 more options, I think I'm gonna go with the WM873. Oh, best part, this library, mentioned it earlier, it's coming back. Oh, womp womp. That's okay. Let's see if we can choose a different one. Oh, this one's in here. I'm going to go with, let's do, at least this one's here. Okay, so in this case, we might as well start with putting down what we know we're going to use. I'm pretty confident that we're going to use a module. Simplicity, cost. I mean, we're doing a production run or a prototyping run, proof of concept run of only a couple of these units. So I would say, instead of breaking it out into its individual ICs and then getting all the peripheral components, let's have people do that for us. So 32 S3. Okay, you can see the full power of this library, the shared common parts library. Stock information, manufacturer part number, you can filter by, does it have a datasheet, does it have a model, by manufacturer, did you key mouser, this is a recent feature, and then components with manufacturer part numbers. Great, all right, let's do that. And our first part is laid out. Now, this is where the fun starts to happen. Once you have a project on the canvas, we can start asking Copilot questions about that part. For example, I'm going to be proactive in this. List out all the, actually, let's do in one, so you can see what I'm typing. There we go. In U1, list out GPIOs. And let's see. We know that this has a datasheet because, oh, I don't know if we filtered by that. Let's see if it does. a joyous day. Indeed it does. Wonderful. There should be the information that we're looking for right in here. And let's see if Copilot can figure it out. While he does that, let's go in here. Try and find an integrated BMS and charging IC. I think that would be the best bang for the buck. We're trying to make this simple. We're trying to make this straightforward. We don't need to go and break things out into individual things. Don't overcomplicate if you don't need to. Actually, here comes the really cool part. Now that we have our audio codec, or half audio codec, let's do. Flux net portals function as connections between nets. The net names don't necessarily mean connection, electrical connection. So we use net portals to portal around the canvas. Ah, I see. Right now, those are reserved for the internal flash. Got it. And I know off the top of my head that any of these pins can be configured. Your only bottleneck is that you may not have the full range of communication speed. That's okay. I don't think we're going to be recording anything in too high resolution. It's going to be determined by the actual audio processing, text-to-speech. There's a good chance that it won't get too high. Now you see the use of comments in the canvas. All right, cool. Let's take a look at the battery management systems. Now, there is a part of me that's thinking maybe we don't go with something that is a direct codec. Maybe we can use something that leverages I2S, because we're finding that it's a little difficult to create an audio codec system for this design without leaving the simplicity and inexpensive behind, right? Or, yeah, without leaving it being too much money. Let's see if we can come up with a solution. How many I2S channels does the It seems like we're going to need not just a BMS system, but we're also going to need a buck boost converter. Let's add this BQ gas gauge and recommend 3 different buck boost converters. I'm also more partial to a buck boost converter solution just based on efficiency. We're really trying to get that 6-hour battery life mark. It looks like we found our solution. No more audio codecs Not today. Goodbye. Gone. Gone. I think one of the largest energy sinks in this design may just be the RGB LEDs. This is looking like the IC that's going to bring us our microphones. We're back to evaluating our microphone choice. I wanted to really make sure that this microphone was going to be best suited for this design. Who better to ask than the person or agent who has access to all the information in this design? And that is the Copilot. Copilot came up with the conclusion that the microphone we chose, which is the IC43434, that is the best microphone for this design. And it says for the reason being, I think that deserves celebration. And it says for the following reasons. High SNR ensures audio capture necessary for transcription, sentiment analysis. Again, it's pulling in all of the requirements. This is just so having an agent or basically a custom search engine plus comprehensive partner in your design process is so incredibly valuable, especially when it continuously relates back to the initial design requirements, which in this case it does. Align requirement for long battery life, beautiful. Known to easily interface with the I2S interface of modern microcontrollers, beautiful. This is fantastic results. One more pip array. Let's go take a look and see if we can wire these together. I also asked whether or not it was able to be run off of 3.3 volts, and the answer is yes. It went into the datasheet and it pulled out the necessary information. Now that we have power and ground hooked up, the next step for these microphones is to connect the two I2S buses. And I think we can get Copilot to help us out with this. This is a feature that is going to be explored more with generative schematics. That's a feature coming out. And essentially what this does is it allows Copilot, within the context of your design, to create connections that you approve. You can allow it to take action simply by asking, how would I connect MK1 to the I to S0 bus? Found out that this is not a buck boost converter. This is in fact just a buck converter. And what was fantastic is that it took the, I'm going to throw another one of these up here. It took the question that I asked, what is the quiescent current of this buck boost converter? And it identified that I thought it was a buck boost. In fact, no, it's a buck converter. So let's try and find a buck boost converter that'll work. And what do you know? Full connection. This is correct. Oh, actually, let's double check. Aha. Almost fully correct. I think it got messed up when it came to LR because that is not. Actually, let's make a guess. Connected all of the available pins, I believe, for data out. What is LR? This micro. I have a sneaking suspicion it determines whether it's left or right. But we'll find out. Let's do the same thing for here. Have Copilot take action for us. I think having Copilot generate connections automatically for us based on a prompt is worthy of our confetti. Wonderful. Because we have an additional pin on the I2S bus for U1, we're actually running into an issue where Copilot is assuming that it needs that connection. And I think that's fair. It's looking for a regular GPIO, we can find out here, a standard GPIO in order to select left or right. And now our microphones are all hooked up. And it was as easy as asking Copilot and double checking the answers. Always check. You can't even rely on humans. Everyone makes mistakes, including AI agents. But the really fascinating part is that the mistakes that are made are logically coherent. And the fact that I can understand why a mistake was made makes it so that I can prevent a mistake like this from happening in the future by defining my prompt better, specifying L and R as being a specialized pin for this microphone rather than having it assume that it needed to be connected because it was available. Let us add some decoupling capacitors. Let's do a 10 microfarad for some bulk. 10 UF. This is when when it comes to passive, stock is very important. Price is also very important at quantities. We can actually check, depending on our part, if we come over here and click on this, we see all the properties that are available for this part, manufacturer part number, manufacturer, part name. We also see the quantities and the stock that is available at different companies that we can order from. DigiKey, Mauser, Arrow, and then a few other companies and suppliers. I'm going to be connecting the thermistor to the BQ module right now. I'm going to have Copilot use the connections that I just made and connect it up for me, and then check to see if it's right. I just asked what peripheral components. This is another feature that I like to use Copilot for, and it's to deep dive into the datasheet and find all the peripheral components that are needed to make an IC work the way that you need it to. Previously in the project description, I'd required a charge controller and a battery management system and a gas gauge to monitor the batteries for safe charging because it's going to be close to the skin, and be able to output 3.3 volts. I started with the battery management system. I asked what the peripheral components were: input capacitor to ground, 10 to 22 microfarads, then output capacitor, thermistor. This is just to double check. The thermistor connections are correct, although it did choose the N for the TS. I can change that, but it would work. There are connections required are from TS to ground. That's the thermistor. And it's going to be a 10K thermistor. And then the current limiting resistor for charging for output current. Then there's output charge timer capacitor for safety timeout. And then battery connector enable pin, power connector. I'm going to take a quick break, just grab some more tea, kind of wetten up my vocal cords, gross way to say that, and I'll be back. And I'll get ready to finish up the schematic, and then it's on to layout. Layout's going to be interesting. It's going to be mostly you watching me. I'm not going to really have too much to talk about because Copilot primarily exists within the realm of the schematic, because in all honesty, most design time and most of the difficult decisions really surround the architecture and the schematic. So we'll do some design reviews, we'll do some last minute touch-ups to the schematic, connecting everything together, grabbing those peripheral components, bringing them in, doing the calculations for that buck boost, and we should be good to go to start layout. All right, I'll see you in 1 second. And we're back. So where we left off was we're looking for the USB-C connector. You're going to find me focusing down on getting the power system up and running on the schematic, doing the calculations for the buck boost, and getting the peripheral components for the gas gauge, or the battery management system. All right, time to focus down. An important note: when you're designing something like a buck converter, boost converter, any type of switch mode power supply, it's really important that the calculations are checked once, twice, thrice. Going through the avenue of using an AI agent to assist you in these calculations is really helpful, not just for the initial calculations, but also for the checking of the calculations. So what I just did is I asked Copilot to approximate the overall power consumption or the current draw of this design max operating at the peak current draw. This is so that I can properly size the inductor that I'm going to choose for the buck-boost converter. After I got the confirmation for an approximate power consumption, so approximate peak load conditions of this design, which went through and detailed each of the steps and where it was finding the power draw, it came to about 1.1 amps at peak. There's no way that we're going to get anywhere close to that, and I do see and recognize now that one of the largest draws will be the RGB LEDs. That being the case, I'm currently debating a design choice which will limit the RGB LEDs to only 1 or 2, just to indicate different statuses. I'll get back to you. And now I'm going to add the final component to this design, which is a micro SD card slot. This should round out the entire schematic, providing a USB-C connection for charging and some data input and output, a ESP32 S3 module, which has Wi-Fi and Bluetooth. It has 2 microphones using I2S communication, 1 battery management system, 1 buck boost converter to convert to 3.3 volts, and that is the system, plus the SD card. Then we can start going through a design review and ending with layout. I'm going to start design review checking every single aspect of this design, making sure that I haven't missed anything. I'm going to leverage Copilot AI to go into the data sheets of each of the components that I've added each of the ICs that I've added peripheral components to, and making sure that maths. I started with U2, which is the buck boost converter. I'm making sure that the inductor is sized correctly. I'm going to check if the output capacitance is sufficient, the diode is sufficient, and the feedback network is sufficient. I'm actually going to do those one after another. And so there's a take action button if I wanted to reroute any of the connections, but the conclusion is that the inductor, based on the saturation current, the peak current, the average voltage, it is a suitable inductor selected for this design. After checking the output capacitance, it seems like there is insufficient output capacitance for this design. In order to improve this, I'm going to add another 22 microfarad capacitor. After adding that additional output capacitor and connecting up from the output of the battery management system to the input of the buck boost converter, I'm now going to check the voltage divider and bootstrap capacitor. Checking the resistor divider one more time for the feedback, just to make sure we really get that 3.3 volts. It seems that we are at 3.3 volts. Now, after checking the reference design of this BQ, I see that I need to add some pull-up resistors to charge, power good, and some pull-down resistors to, oh no, a pull-down resistor to LAM to set the output current max. I asked Copilot to calculate for me the output current resistor, and I will double check that math again with AI. And with that final placement of tying the timer capacitor to ground to set an unlimited time, I say that the battery management system is ready for design review. So I'm going to go through the same process, ask each individual peripheral component to be checked against the datasheet to make sure all components were calculated correctly, all pull-up and pull-down resistors are configured correctly, in which case, once that's done, and once the micro SD card is done, perfect. I will begin doing the layout. Current time is around 2 hours, 2 hours and a half. I'll throw up that timer on the speed run. And once we get to the layout, it's going to be a pretty straightforward process since we're going to do a 4-layer PCB that's going to be around 5 centimeters in diameter. It's going to give us a lot of room to play with. And oh, one more thing, I have to add the LED. So once I add the LED, throw on the GPIO, we should be wrapping up. That was fun. It seems as if the entire schematic is put together. I've included all the pieces. and now it's onto the layout. So this is where AI kind of takes a sidestep and stays on the schematic. We will be going back and forth from the schematic to the PCB just to make sure that we chose the right connections. It's a big module, as you can see in the PCB tab. It's a relatively big module for what we're designing, but that gives us the ability to customize where our GPIOs are so we can do a better job and more intentional job with placement. This is going to be the part of the video that gets pretty quiet, so sit back, relax, enjoy the beats, and watch the layout happen before your eyes.
だけが読み直している読み直している読み直している読み直している読み直しているテキストしたい人読み直している読み直しているだけが読み直している
Hey, just jumping back in real quick, I wanted to let you know that I am going to be changing the inductor. It seems like the footprint is just too big for our form factor, and these are the trade-offs that we have to make. I'm going to select one that has the same, just as we determined in the review process, that has the same inductance properties and electrical characteristics so that they match roughly. We might get some higher parasitic resistance, or DCR, excuse me. We might get some similar DCR, some larger DCR by switching to a smaller size, but since we are only really looking at a saturation current of 500 milliamps, we really shouldn't be anywhere within the realm of needing something this size. So these are the decisions you have to make in the middle of the layout. And we've finished. This did take a little bit longer than what was initially anticipated, but it's an entire product. I could go get this fabbed and I would have an AI pendant that has the capacity to record my voice, speech to text, use AI sentiment analysis for things like how many insults did you receive in a day? How many compliments did you give in a day? What were your action items that you had after your meeting? All these things can be recorded, organized, and then sent to your phone in this one product. And with Copilot, I was able to do it in 3 hours, give or take 30 minutes. If I wasn't talking so much, maybe I would have been able to get it done in 2. So this just goes to show you the power of having generative AI at your fingertips, especially when you're designing a board like this. I am going to go take a nap, and I will see you guys in the next speedrun. Thanks.